In question 1, I want to find dy dx in two ways, by using implicit differentiation, and then the other way is to solve this equation for y, and then differentiate that brand new equation. So for starters, I'm going to take the derivative of both sides with respect to x. So this is by implicit differentiation. I see that I have a product of two functions, so to start with, I'm going to use the product rule. That's the derivative of the first times the second, plus the first times the derivative of the second. I add on the derivative of x, which is 1. I add on the derivative of x squared, which is 2x, and this is equal to 0. We're definitely not going to have enough room to fit all of this in one slide, so I'm just going to move this problem to the next slide. All right, so looking here, I want to solve for y prime, this thing. What I'll do is subtract these terms to the other side of the equation. I get x times y prime is equal to -1 minus 2x minus y. And if I divide both sides by x, I get that y prime is equal to -1 minus 2x minus y all over x. And that's an acceptable answer. Okay, but another way to do this would be to solve this original equation for y. Take this thing here. So here's a second approach. We'll solve for y, and then take the derivative of that new equation. Okay, so this way, if I'm solving for y, I'll subtract x and x squared from both sides. So let's see, I get xy is equal to 1 minus x squared, and then I'll divide both sides by x. And I get that y is equal to 1 minus x squared all over x. And I can actually break this up into 3 fractions. And since I want to take a derivative, I'm going to make the first fraction x to the -1. Okay, so I split this up into 3 fractions. X into 1 is 1 over x over x is 1, and x squared over x is just x. Okay, if I want to take the derivative of this, okay, let's see what we get. Y prime is equal to -x to the -2. Then the next term is 0, and then I get -1. This thing. Are these two equations equal? They don't look equal, but are they in fact the same thing? Well, one way we could figure this out is by taking this value of y, putting it here, and then seeing if the two equations are in fact the same. So let's check this just to see if our answers do match up. Are these two things actually equal? So are these two derivatives actually the same thing? And here I have the two different derivatives, and my original equation when we solved it for y was 1 over x minus 1 minus x. To show that these are equivalent, in place of this y, I'll put the original function, I'll simplify it, and see if we get this thing over here. So let's do it. Y prime is equal to -1 minus 2x minus y, which is 1 over x minus 1 minus x. So y prime is equal to, let's see, -1 minus 2x minus 1 over x plus 1 plus x. Okay, we got some stuff that combines and cancels, like this negative and positive 1. So that's gone. Y prime is equal to, okay, we have a negative 2x and a positive x, that's negative x, and then minus 1 over x, all divided by x. We can break this up into 2 fractions. This x goes into this x, and you have -1 left over. So we have y prime is equal to -1. Then you have minus, and you're taking 1 over x and dividing it by x, which puts it into this denominator, so it's 1 over x squared. And if you change that so the exponent is negative, well, -1 over x squared is -x to the -2 with a -1 left over, and we have that these two derivatives are in fact the same thing. For part B, same idea. Let's find the derivative implicitly. So we get 2x plus 2y times y prime is equal to 0. I'll subtract 2x from both sides. And we get that 2y times y prime is equal to negative 2x. I will then divide both sides by 2y. And we get that, let's see, y prime is equal to negative x over y. And this is the derivative. Another way, probably a longer way to do this, is to solve this equation for y and take the derivative of that thing. So here, we're going to first solve for y. When we do that, we get that y squared is equal to 4 minus x squared. You then have to take the square root of both sides. And we get that y is equal to the square root of 4 minus x squared. And technically, you get two solutions, a positive and a negative. I think we can still differentiate this with that plus minus in front of it. In fact, before we take the derivative, I'm going to write this as y is equal to plus or minus 4 minus x squared to the 1/2 power. So y prime would be equal to, we get plus or minus 1/2, we get 4 minus x squared to the negative 1/2, and by the chain rule, I have to multiply by negative 2x. This thing. If I simplify this, let's see, I get that y prime is equal to, well, I can cancel some stuff. I have this 2 and that 1/2 that cancel. This negative can be somewhat combined with this plus or minus. I mean, really, it just makes it maybe a minus plus. I'm going to actually include it just because I see a negative in my answer over here. Might be kind of a funny way to write this, but I'm going to put that first negative out front. Then we have this plus or minus. We have 4 minus x squared to the negative 1/2, and this whole thing is multiplied by x. What I'm going to do is leave the negative alone. I see I have a negative exponent, so I'm going to think fraction. And I'm going to take this whole thing and put it into the denominator with a positive 1/2 exponent, which is the same thing as saying a square root. That means I can leave the x alone and put it in the numerator. So this whole thing went to the denominator. This plus or minus, I can actually tag it along and put it right here. So I'll put that plus minus here. Because a fraction is positive or negative if the denominator is positive or negative, so it doesn't matter if this is in the numerator or the denominator, so I'll put it here. Here we go. This is the derivative. There's technically two answers. There's negative x over the positive square root of 4 minus x squared, and the derivative is equal to negative x divided by the negative square root of 4 minus x squared. Why are these two things the same? Well, y is identical to plus or minus the square root of 4 minus x squared. I mean, I don't have to do much more work than to say, all right, are these equal? The answer is yeah, because y prime is equal to negative x over, and this entire denominator is the same thing as y. So yeah, they are in fact the same thing. Before I take the derivative of both sides, I'm going to write this as y to the 1/2 plus x is equal to 1. Taking the derivative with respect to x of both sides gives me 1/2 y to the negative 1/2 times y prime, plus 1 is 0. I can subtract 1 from both sides. I get 1/2 y to the negative 1/2 times y prime is equal to negative 1. I can divide both sides by this 1/2 and this y to the negative 1/2. So I'll divide all that stuff to both sides. And what I end up with is the derivative is equal to negative 1 over 1/2 y to the negative 1/2. I think it is worth simplifying this thing. This I can move to the numerator by making the exponent positive. And if you're dividing by half, that's the same thing as multiplying by 2. So let's write this as y prime is equal to negative 2y to the 1/2. And if you don't want that 1/2 symbol, you could also put negative 2 the square root of y. Either is fine, and that is the answer by using implicit differentiation. Okay, well, what about taking this equation and solving for y? Well, to do that, my first step is going to be to subtract x from both sides. So I get this. And if I want y by itself, I will square both sides. And I get y is equal to 1 minus x squared. Okay, if I now take the derivative of this thing, I get y prime is equal to, on the other side I have to use the chain rule, that's 2 times 1 minus x to the first times negative 1, and that's it. Probably not the best way to write it, so I think what I'll do is put y prime is equal to, I'll put that as negative 2, and I'll put 1 minus x, and I'll just leave off that exponent of 1, this thing. Are these two in fact equal? And the answer is yes. If you look here in your original equation, we said that since y, the square root of y plus x is equal to 1, the square root of y is equal to 1 minus x. If you substitute 1 minus x with the square root of y, you get negative 2 square root of y. So these two things are in fact the same, so both methods take us to a solution. The same solution. Let's find the derivative by using implicit differentiation. So to start with, I'm going to rewrite this equation as 2 times x to the negative 1 plus 3 times y to the negative 1 is equal to 4. If I now differentiate both sides with respect to x, I get negative 2x to the negative 2 minus 3y to the negative 2, but I have to multiply by y prime, and that's equal to 0. To solve for y prime, so I want to solve for this thing here, I'm going to add 2x to the negative 2 to both sides. And I get that y, negative 3y to the negative 2 times y prime is equal to 2x to the negative 2. I can divide both sides by negative 3y to the negative 2. They cancel on the left, and all I'm left over with is the derivative. On the right, the whole answer is negative. It's a fraction with 2 and 3 as 2/3. But these exponents are negative. I can move the y up here and the x down here, provided that I make their exponents positive. So that's y squared over x squared. And this is my answer. But what if we didn't want to use implicit differentiation? We'd have to solve this for y. I think to do that, I'm going to subtract 2x from both sides. And if I'm solving for y, I'm going to call the entire right side a fraction over 1, because if I flip this fraction, then I can flip this fraction to get y into the numerator. So this is y over 3 is equal to 1 over 4 minus 2 over x. To get y by itself, I'm going to multiply both sides by 3. So I get that y is equal to 3 over 4 minus 2 over x. And I don't like fractions within fractions, so I'm going to multiply the top and bottom by x, canceling the fraction within the denominator. So I get y is equal to, okay, I have 3x over 4x minus 2. Now that's just y. That's not the derivative of it, so I still need to take the derivative. And the way I'm going to do that is by using the quotient rule. I think we can start that on this slide. but just to make a note of this, I want to use the quotient rule. And hopefully the derivative I end up with will be equal to this thing. The quotient rule says that the derivative is, well, I start by taking the derivative of the top and I multiply by the bottom. I then subtract the top but multiply by the derivative of the bottom. And I divide this whole thing by the bottom squared. If I simplify this, maybe make a substitution, it should be equivalent to this. Let's check it out on the next slide. So here's my derivative. It's not simplified, but I see I can multiply in the 3. And so I get that y prime is equal to 12x minus 6 minus 12x, okay, all over 4x minus 2. And interestingly, those 12x's cancel, and I have that y prime is equal to negative 6 over 4x minus 2 squared. Now, is this equivalent to our other derivative? And a reminder, our other derivative was y prime was equal to negative 2y squared over 3x squared. Are these the same? Well, we have to recall what y is. Y was equal to 1 over, actually, I think we reduced it so it was y was equal to 3x over 4x minus 2. I'll put that in place of this y. I'll simplify it. Hopefully I get this. Let's see what happens. Negative 2. Oh boy, squaring this is going to be squaring a fraction. This thing. Okay, if I square this fraction, I can square the top and the bottom separately. And this part's going to be 9x squared. And this part I'm going to leave as 4x minus 2 squared since I see it over here. So the derivative is, well, the whole thing is negative. It's 2 times 9x squared over 4x minus 2 squared. And this is all over 3x squared. So I just squared the top and bottom of this to give me this. Okay, we'll move in this direction here. Okay, y prime is equal to, so again, it's negative. Oh, okay, this is negative 18x squared all over 4x minus 2 squared. And this 3x squared can move into the denominator of this fraction. I can cancel the x squareds. 3 goes into 18 6 times. And what we're left with is that the derivative is equal to negative 6 over 4x minus 2 squared. I mean, this verifies our work. Both ways are equivalent. In question 2, we want to find y prime. And by that, we mean the derivative of y with respect to x. So we're not going to also solve for y. We're just going to simply get the derivative. Starting on the left, the derivative of 4x squared is 8x. The derivative of 9y squared is 18y times y prime. And this is equal to 0. I will subtract 8x from both sides. And I get that 18y times y prime is equal to negative 8x. Okay, I think my next step is to divide both sides by 18y. And that isolates the y prime for us. Y prime is equal to, okay, we get negative 8x over 18y. I see there's a factor of 2 that can be reduced. That means we get negative 4x over 9y. And this is my answer. So again, just to point out, we got this y prime after we took the derivative, and then we just solve for it thereafter. If we take the derivative of both sides with respect to x, we get 4x minus 2y times y prime is equal to 0. My goal is to solve for this derivative, y prime. So I think what I'll do is subtract 4x from both sides. And we get negative 2y times y prime is equal to negative 4x. I will divide both sides by negative 2y. And we get that y prime is equal to negative 4x over negative 2y. Of course, we can reduce this a little bit. This is going to be 2x over y. And that is the final answer. The derivative of the left is going to be, well, the derivative of y is y prime. The derivative of x is 1. The derivative of y squared is 2y times y prime. On the right, we get 0 for the 1. The derivative of y is y prime. And then the derivative of that minus x is minus 1. Kind of a curious thing that happens here. Since there's a y on both sides, there's a y prime on both sides, those actually just cancel. And what we want to do is solve for this y prime. I think my approach will be to subtract 1 from both sides. And I get 2y times y prime is equal to negative 2. I can now divide both sides by 2y. And I get that y prime is equal to negative 2 over 2y. Those 2's cancel, and I get negative 1 over y. And that is the final answer. I'm noticing in this problem that we have a product of two functions. We have this 4x multiplied by a y, so I want to be careful and make sure I use the product rule here. The derivative of the left is 3y squared times the derivative of y plus, okay, the derivative of 4x is 4, and we multiply it by y. I add on the 4x and multiply by the derivative of y. The derivative of x squared is 2x, and the derivative of 10 is 0. My goal is to solve for y prime, and here I actually have a couple of them. I want to leave those two terms on the left side of the equation, but I'm going to subtract 4y and 2x from both sides of my equation. I get 3y squared times y prime plus 4x times y prime is equal to negative, doesn't matter the order, but I'll put minus 4y minus 2x. On the left, I can factor out a y prime, and what is left over is 3y squared plus 4x. That means I can now divide both sides by this 3y squared plus 4x. And I have my answer. It's a mess, but y prime is equal to, okay, we get negative 4y minus 2x all over 3y squared plus 4x. And that's as far as I'll take this one. I'm seeing a couple more products in here. So like I have a x cubed that's being multiplied by a y squared and a y multiplied by cosine of x. Starting with the x cubed y squared, the derivative of x cubed is 3x squared times y squared plus, okay, I leave the x cubed alone, but multiply by the derivative of y squared, which is 2y times y prime. Okay, then I add on to that. Okay, I take the derivative of the y, that's y prime. I leave the cosine of x alone. Then I leave the y alone, but multiply by the derivative of cosine of x, which is minus sine. And the derivative of the other side is simply 0. Right, here it is. Let's see, I have a y prime here and here. I want all the other terms on the other side of my equation. Maybe I'll just like rewrite this a little carefully. This is 3x squared times y squared plus, I'll put this next thing as 2x cubed y times y prime. I'll write this next thing as cosine x times y prime. And that's really minus sine x times y. So the stuff that I am subtracting to the other side is this 3x squared. Let me erase that. This thing. And also this I'm adding to both sides of my equation. So like over here I'm doing minus 3x squared y squared, but I'm also adding sine x times y. Okay. On the left, what I have left over is 2x cubed y times y prime plus cosine x times y prime. And that's it. On the other side, I have negative 3x squared y squared plus sine x times y. On the left, I can factor out the y prime, and what is left over is 2x cubed plus cosine x, that is still equal to negative 3x squared y squared plus 2 sine x times y. Divide both sides by 2x cubed plus cosine x. And I have my answer. My answer is, the derivative is negative 3x squared y squared plus sine x times y all over 2x cubed plus cosine x. And that's it. I see there's a couple of products. So again, I want to use the product rule on the left. Okay, we have x cubed y squared, and then we have x cosine y. Pretty similar to the previous question, but we get 3x squared times y squared plus x cubed times 2y times y prime plus 1 times cosine of y plus x times the derivative of cosine of y is negative sine y times the derivative of y. This is equal to 0. All right, let's simplify this a little bit, or at least rewrite it. We get 3x squared y squared plus 2x cubed y times y prime. Here I'm just going to put cosine of y, and I'll call this minus x sine y times y prime, and that's equal to 0. The y primes are here and here. Okay. What now? Okay, so what I want to do is subtract this 3x squared y squared from both sides. And I also want to subtract this cosine of y. And what I get is 2x cubed y times y prime minus x sine y times y prime is equal to negative 3x squared y squared minus cosine of y. I'll factor out the y prime on the left. And I'm going to divide both sides by this stuff. And I have my answer. Y prime is negative 3x squared y squared minus cosine of y all over 2x cubed y minus x sine y. And that's it. I'm going to copy this problem down again, just to, for emphasis, note that we have a composition of two functions. So when I take the derivative of this left side, I first start by taking the derivative of tangent, which is secant squared of xy. By the chain rule, I need to multiply by the derivative of xy. The derivative of x is 1. Copy down the y. Copy down the x and multiply by the derivative of y. The 1 has a derivative of 0, and on the right side of my equation, the derivative of e to the x is e to the x. And I'm going to multiply this to both terms in the parentheses. This is not the only approach to take, but that's just the first thing that jumped out at me. When I do that, I get y times secant squared of xy plus x secant squared xy times y prime is equal to e to the x. And here, this is the derivative that I'm solving for. Okay, I will subtract y secant squared xy from both sides of my equation. And what I have left over is x secant squared of xy times y prime is equal to e to the x minus y secant squared of xy. Nothing to factor out. In fact, I can just divide both sides by x secant squared of xy. And I have my answer. Y prime is e to the x minus y secant squared of xy all over x times secant squared of xy. And that is it. To take the derivative of the left, I see that we have a product of two functions, so I'm thinking product rule. The derivative of sine of x is cosine of x, and we leave cosine of y alone. And then add on, okay, sine of x is left alone, but the derivative of cosine of y is negative sine y times y prime. And on the other side, the derivative of 1 is 0, and the derivative of x is 1. Let's simplify this a little bit. This is cosine x times cosine y minus sine x times sine y times y prime is equal to 1. I'm solving for y prime. So I think I will subtract cosine x cosine y from both sides of the equation. And I get negative sine x sine y times y prime is equal to 1 minus cosine x cosine y. I can divide both sides by this negative sine x sine y. And I have my answer. Y prime is equal to 1 minus cosine x cosine y all over negative sine x sine y. You could move this negative into the numerator, making it a -1 and a positive here, but I mean, really, this is completely fine, and I'll say that this is the simplified answer. All right, let's rewrite this one again. This is e to the x cubed y is equal to 1 minus y. I'm doing this because I'm noticing on the left side of my equation, I have a composition of two functions. Therefore, I'm using the chain rule. For the derivative of the left, the derivative of e to anything is e to that thing. But by the chain rule, you have to multiply by the derivative of what was composed in the function. So that's the derivative of x cubed y. The derivative of x cubed is 3x squared times y plus x cubed times y prime. On the other side of my equation, the derivative of 1 is 0. The derivative of negative y is this, y prime. Okay, if we're solving for y prime, well, first I see there's y primes on both sides of the equation. But what I think I'll do is distribute this in first. I'll rewrite this thing as 3x squared y e to the x cubed y plus x cubed times e to the x cubed y times y prime. This is equal to negative y prime. So I want to solve for the y primes. Okay, let's see. I think I'll add this to the left and subtract this to the right. So I'm going to do that all in one step. This becomes the following. We get x cubed e to the x cubed y times y prime plus y prime is equal to negative 3x squared y e to the x cubed y. Again, that was, I added this to the left and I subtracted this to the right. I'm going to factor out the y primes and divide by what is left over. We get y prime times x cubed e to the x cubed y plus 1 is equal to negative 3x squared y e to the x cubed y. When I solve for y, I get the following thing. Actually, I'm going to write the divided by part. So I'm really dividing both sides by this. I'm running out of room for it, but I'll put it up here. Y prime is equal to negative 3x squared y e to the x cubed y, all divided by x cubed e to the x cubed y plus 1. And that is it. I'm going to start by rewriting the left side of this equation so we have a 1/2 exponent. So this is xy to the 1/2. And that's equal to cotangent of y and then plus x. Also, this xy is a product. So here we have a composition where we have to use the product rule. Okay, so let's start by taking the derivative of the left. I bring down the 1/2, copy down the inside, subtract 1/2 from the exponent. But now I have to multiply by the derivative of xy, which is 1 times y plus x times y prime. On the other side of the equation, we have the derivative of cotangent, which is negative cosecant squared of y. But we have to multiply by the derivative of y. And then I put plus 1. So I think what I'll do is distribute all of this into the parentheses, simplify it a little bit, and then solve for y prime. Okay, we get 1/2 x y to the negative 1/2 times y plus 1/2 xy to the negative 1/2 times x times y prime. That is equal to negative cosecant squared of y times y prime plus 1. And I see we have a couple of y primes. There's one on this term, and there's one on this term. So my approach is going to be, I'm going to subtract this to the left side of the, I'm going to add this to the left side of the equation and then subtract this to the right side. Let's do this all in one step. We get left over on the left, 1/2 xy to the negative 1/2 times x times y prime plus cosecant squared of y times y prime. This is equal to, on the right, left over we have 1, and we moved the 1/2 x y to the negative 1/2 y. I'm going to factor out the y prime, and I'm going to divide what is left over to the other side of my equation. I'm going to do that all in one step as well. So I'm factoring out the y prime. I can now remove that. Now on the right, I'll have 1 minus 1/2 xy to the negative 1/2 times y. This whole thing is divided by what was left over on the left side of the equation, which is 1/2 xy to the negative 1/2 times x. And then plus cosecant squared of y. And this is my final answer. Let's rewrite this problem so there are no fractions, but everything is instead a product. So on the left, this is x times y to the negative 1, then plus, okay, the x comes up, but the y is in the numerator, so I get this. And then we get x plus y to the negative 1 times y. Written this way, we can now use the product rule instead of the quotient rule. Let's see what happens. Starting with the first term, okay, the derivative of x is 1, and we leave the y to the negative 1 alone. We then add on, I have the x, but I multiply by the derivative of the second thing, which is negative y to the negative 2 times y prime. Okay, next, let's see, the derivative of x to the negative 1 is negative x to the negative 2, and then I multiply by the second, and then I leave the first thing alone, and I multiply by the derivative of the second. I'm not going to have enough space, so I'm going to put an equal sign and continue my work over here. I'm taking the derivative of this, so starting with the first piece, I bring the negative down, I copy down the x plus y and raise it to the negative 2, but then I have to multiply by the derivative of what is inside the parentheses. Okay, the derivative of x is 1, and the derivative of y is y prime. Okay, then I copy down that y, the second thing here, just the y, copy it down. And then I add on, okay, leave the first thing alone and multiply by the derivative of the second, and I get this. This mess. So I have a y prime, I have a y prime, and a y prime. They're everywhere. I think it'll be beneficial to simplify this. Okay, so we have y to the negative 1 minus x y to the negative 2 times y prime minus x to the negative 2 times y plus x to the negative 1 times y prime. That is this side of the equation. Okay, over here, again, something strange is happening. I'm going to have to multiply this y into the parentheses, but I'm going to have to multiply this into the parentheses as well. I'm going to do this all in one step. In fact, let me start blocking this off. So there was my first line. That was my second line. So what I'm going to do is erase this equal sign and put it right here just because I think there's going to be a lot of terms on this side. So over here, what I'm going to do is multiply not only this to the 1, but I'm going to multiply this y to the 1 as well. Okay, so we get negative y times x plus y to the negative 2. That was all multiplied to the 1. And I'm going to do the same thing for this y prime. So we get another negative y x plus y to the negative 2 times y prime. And then lastly, I'll just copy down this x plus y to the negative 1 times y prime. Okay, that stuff. Where are the y primes? There's one here, 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 and here. Okay, I want all of those on the left side of my equation. So I'm going to move these over, and I'm going to move this to the other side. Okay, let's see if I can actually fit all of this in here. Here we go. So on the left, I have the negative xy to the negative 2 times y prime. I then have plus x to the negative 1 times y prime. I'm going to move this here, making it a positive. So that is plus y, x plus y to the negative 2 times y prime. And I'm subtracting this to the other side. So I get negative x plus y to the negative 1 times y prime. The stuff that got moved to this side of the equation was I have to subtract this, so I get negative y to the negative 1. I need to add this to both sides, so we get plus x to the negative 2 times y. And then this piece didn't go anywhere, so it stays on the right side of the equation. So we get negative y, x plus y to the negative 2. From here, I factor out the y primes. It's 4 of them. And I'm going to divide the remaining stuff to this side of the equation. So I'll put that on the next slide. So here's what I got. There's a chance I may have missed something, but I think I copied everything down correctly. What is up here what is left over on the right. The stuff that's down here is what was left over after I factored out the y prime on the left. If I take the derivative of the left, the derivative of secant is secant tangent. So that means we get secant of x minus y times tangent of x minus y. But by the chain rule, I have to multiply by the derivative of x minus y, which is 1 minus y prime. Now, on the other side of my equation, I see I have a fraction, so I'm actually going to use the quotient rule. It's not necessary, but, let's try it out. Let's see what happens. Okay, if I use the quotient rule, the derivative of the top is e to the y times y prime. I then copy down the denominator. I then subtract off the numerator times the derivative of the denominator, which is 1. And this is all divided by 1 plus x, quantity squared. So in solving for y prime this way, I see there's a y prime here, there's a y prime here. Okay, I suppose what I'll do is multiply in this secant tangent to both terms. And then I think I'm actually going to break this up into 2 separate fractions. Let's see what this turns into. We get secant x minus y times tangent of x minus y times 1. I won't write the 1, but then I have to multiply it to the y prime. So we get secant x minus y times tangent of x minus y times y prime. I'll put an equal sign like this just because I'm running out of room to write my work. On this side, I'm going to divide the x plus 1 to both terms in the numerator. So we get, I'm going to write this as e to the y. An x plus 1 over x plus 1 squared leaves me with just an x plus 1 in the denominator, or 1 plus x, I should say. And then we have a y prime left over. On my next term, I have e to the y divided by 1 plus x squared. My y primes are here and here. Okay, so for the next part of this work, I'll leave this alone. I'm going to subtract this to the left. I'm going to subtract this to the right. I'm going to swap them. Let's see what we get. I get negative secant x minus y tangent of x minus y times y prime minus e to the y over 1 plus x times y prime. On the right, I have, again, I'm running out of room, so maybe I'll just drop it down like this. Okay, on the left, this gets moved over here, so it becomes negative. It's x minus y. And then on the right, I already have this e to the y over 1 plus x squared. What I'll do is factor out the y primes and divide what is left over to the right side of the equation. So this is the answer after I factored out the y prime on the left and divided what was left over to the right side. The numerator and the denominator are almost identical, except here I have a 1 plus x squared and here I don't. But I'm sure this could be simplified, fractions within fractions, but I'm just going to leave it like this. In question 3, we are looking for not dy dx, but dx dy. So essentially, we're going to treat y as the independent variable and x as the dependent variable. So I'm actually going to use the symbol dx dy in my explanations. Let's try it out. Okay, starting with the 4x squared, well, we treat this as bring down the 2, so you get 8x. But since we're taking the derivative with respect to y, I'm going to multiply by the derivative of x with respect to y. So it's just like what we were doing with the y, except now it happens for the x variable. Now here, if you're taking the derivative with respect to y, your answer is going to be 18y, and that's it. Technically, you get a dy dy, which is 1, and we just don't write it. On the other side of my equation, we have 0, and that's it. Okay, I want to solve for dx dy, so I'm going to subtract 18y from both sides of my equation. I get 8x dx dy is equal to negative 18y. I'm going to divide both sides by 8x, and I have my answer. Dx dy is equal to negative 18y over 8x. I see this can be simplified a little bit, so I guess I'll do that. Dx dy is equal to negative, 2 goes into 18 9 times. It goes into 8 4 times, and then this is my final answer. Same thing here. I want dx dy instead of dy dx. Starting with the left side of my equation, I get 4x times dx dy. And if you want to use x prime as a shortcut, that's fine. Now, since we're taking the derivative with respect to y, we get minus 2y, and that's it. And the other side of my equation is going to be 0. I'm going to solve this by adding 2y to both sides. I get that 4x times dx dy is equal to 2y. I can divide both sides by 4x. And I get that dx dy is equal to, we get 2y over 4x. Of course, this can be simplified to y over 2x. And that is my final answer. For this problem, we're taking the derivative of x with respect to y. So if we look at the left side of this equation, just be a little bit careful, it's a cosecant of xy. And this xy is a composition. It's composed in the cosecant function. So the first thing is, well, what's the derivative of cosecant? The formula is it's negative cosecant times cotangent. And that's of whatever was composed in the function, which is xy. By the chain rule, you have to multiply by the derivative of xy. So the derivative of x is dx dy, and then we leave the y alone. We add on, now we leave the x alone, but multiply by the derivative of y with respect to y, and that's 1. I then add on, here we come across an x, and the derivative of x with respect to y is dx dy. The other side of my equation is actually just going to be 1 plus 0, this thing. Okay, I see we have a couple of these derivatives of x with respect to y. So what I'll do is distribute all of this stuff into the parentheses and see what we get. Okay, that's negative cosecant xy, cotangent xy, times y, times dx dy. Then we're also multiplying that to this next part, so we get negative x cosecant xy cotangent xy. Then we have plus dx dy, and this is equal to 1. So I think I'll leave these two terms on the left, and I'll add this to the other side of my equation. So we get negative cosecant xy cotangent xy times y times dx dy. Then we get plus dx dy. That's equal to 1 plus x times cosecant xy times cotangent xy. I'm going to factor out this dx dy and divide what is left over to the other side of the equation. I'll put that here. On the right side, we have 1 plus x times cosecant xy cotangent xy all over. Okay, and after you factor out the dx dy on the left, you have negative cosecant xy cotangent xy times y plus 1. And that's it. All right, let's rewrite the left side of this as x plus y to the 1/2, and this is equal to y plus 1. And again, we want dx dy. Okay, so what we get here is 1/2 x plus y to the negative 1/2. The chain rule says we have to multiply by the derivative of what is on the inside of this function. And so we get, well, the derivative of x with respect to y, well, that's dx dy. And the derivative of y with respect to y is 1. And the other side of my equation is actually just 1. Okay, what I'm going to do is distribute this into the parentheses. So just to write that out, this gets multiplied to both of those terms. That's 1/2 x plus y to the negative 1/2 times dx dy plus 1/2 x plus y to the negative 1/2, and that's equal to 1. I'm going to subtract this from both sides, and then at the same time, I'll divide both sides by this thing, which is from the dx dy. We have that dx dy is equal to, so we get 1 minus 1/2 of x plus y to the negative 1/2. So that was, this gets moved over here, but then I divide both sides by this number, or this term, and I get 1/2 x plus y to the negative 1/2. And here it is. Let's find the equation of this tangent line. And this is supposed to be at the point 2, -3. I put 2, -9, and that is just a typo. So let's just cross that out and put 2, -3. Okay, for starters, I need to know the derivative at this point. So I have to take the derivative of this equation. Since it's implicitly defined, I will use implicit differentiation. On the left, you get 2y times y prime is equal to 3x squared. If you solve for y prime, you get 3x squared over 2y. If you want to know the slope at this point, I'll put 2 in place of x, and I'll put -3 in place of y. So we get y prime is equal to 3 times 2 squared over 2 times -3. So the slope at the point 2, -3, let's see, this is 4 over 2 is 2. It's going to be -2. We need to know the equation of a line through a point, and I'll use this one. This is the point slope version of the equation of a line. If I plug in the information for the point, that's y minus -3. If I put in the information for the slope, that's -2. and then we have x minus 2. If we simplify this a little bit, we get y plus 3 is equal to negative 2x plus 4. And if I subtract 3 from both sides, I get negative 2x plus 1. And that matches up with this graph. Here it has a y-intercept of 1. It looks like it's going down 2 and over 1, negative 2 slope. All right, let's find the equation of this tangent line at the point, this is pi over 2 comma the cube root of 2. Kind of looks like it's a horizontal line, which means this will be a pretty easy equation. But just to be careful, I'm going to take the derivative of this equation to get the slope of this line at this point. The derivative of y cubed is 3y squared times y prime. Okay, the derivative of sine of x is cosine of x, and that's equal to 0. If I solve for the derivative, I'll add cosine of x to both sides. I'll divide both sides by 3y squared, and I can use this to figure out the slope at this point. In place of y, I'm going to put the cube root of 2. In place of x, I'm going to put pi over 2. So y prime at that point is cosine of pi over 2 divided by 3 times the cube root of 2 squared. This actually equals 0. The reason for this is, well, this denominator is just going to be some number. It's going to be a mess. But cosine of pi over 2 is 0. And there we go. We have the slope of our line. If I want the equation of the line, I'm going to use the point slope form for the equation. My y value is the cube root of 2. The slope is 0, and my x value is pi over 2. This entire side is 0. So if you solve for y, you get that y is equal to the cube root of 2. And that's the answer to this part. Same idea here. What is the slope of this tangent line at the point 0, 0.5? I need to take the derivative of this equation to do that. So for starters, I'm going to rewrite the equation as y to the negative 1 plus x times y is equal to 2. When I take the derivative, I get negative y to the negative 2 times y prime. Okay, now I have to use the product rule. The derivative of the first is 1. I copy down the second. I then leave the first alone and multiply by the derivative of the second, and that's equal to 0. I need to solve for y prime. So what I'm going to do is subtract this to both sides. Let's see, I get negative y to the negative 2 times y prime plus x times y prime is equal to negative y. I'll factor out the y primes and divide what is left over to the other side of my equation. What is left over is negative y to the negative 2 and this x. It might not be the best way to write this equation, but can we actually figure out the slope at this point? Maybe I will rewrite this a little bit. The derivative is equal to, okay, this is negative y over, and a y to the negative 2 is 1 over y squared. And then I have plus x. I don't like the fractions within fractions, so I'm going to multiply the top and bottom by y squared to completely clear the denominator within this denominator. And this changes my equation to, we get negative y cubed over negative 1 plus xy squared. If I want the slope of this line, I'm going to put 0 in place of x and 0.5 in place of y. That's negative. Okay, we get 0.5, and we're cubing that, and we're dividing it by negative 1 plus, well, that's actually all going to be 0. This is positive whatever 0.5 cubed is. Is that 0.125? It is. That's not very steep, but this line is not very steep. My equation is going to be y minus the y value is 0.5. That's equal to the slope times x minus 0. If you solve for y, this is 0.125x plus 0.5. And that's it. It looks like I left the point off of this equation, but the one I was referring to was the point 1 comma 1. If we want to figure out the slope of that tangent line and the actual equation itself, I need to take the derivative of my equation. I get 3x squared plus 3y squared times y prime. And on the other side of my equation, I have to use the product rule. So that's 1 times y plus x times y prime. And here my goal is to solve this equation for my y primes. What I'm going to do is move all the y primes to the left. So I get 3y squared times y prime minus x times y prime is equal to y minus 3x squared. If I factor out the y prime and divide what is left over to both sides of my equation, I get this. If I want the slope of this line, I will plug in the point 1, 1 for the x's and the y's. All right, so the slope is going to be equal to 1 minus 3 times 1 squared over 3 times 1 minus 1. Okay, so that is 1 minus 3 over 3 minus 1. I see, that's negative 2 over positive 2. That is a slope of negative 1. Using this form of the equation of the line, the point slope form, we get y minus 1 is equal to negative 1 times x minus 1. So we get negative x plus 1. Y is equal to negative x plus 2. And that definitely matches with what is in the graph. This is the same equation that was in question for part C. I thought it was interesting enough that we should examine it a little bit further. And well, for starters, what is the equation of the line tangent to this curve at the point 1, 1? So like right here. Now you can definitely draw a tangent line there, but it looks like it might be like a vertical line. So what would the slope, what is the slope of that line? If you try to put that information into this equation, you would get negative 1 cubed over negative 1 plus 1 times 1 squared. I'm going to see what's happening here. This is, negative 1 over 0, and this is an error. In fact, you could think of this as something becoming infinite if you divide by 0. You cannot write a vertical line like this of the form y is equal to mx plus b. Can't be done. So you can't do that for this problem. It's no good. However, this is a line, and it does have an equation in the xy plane. The way that you would write a vertical line is of the form x is equal to a number. And it's going to be the number that corresponds to this x coordinate, which is also 1. So this would be the equation of that line. The important thing is that it matches up with the formula in that if you plug in this information, you should get an undefined slope. And you do. You get 1 over 0. There's no number for that. And that's why we can't use this equation, but we can use this one. I also asked what happens to this derivative as x goes to negative infinity. And if you look at the graph, it looks like it starts to level off, like the slope keeps getting closer and closer to 0. If you examine this equation, so let me just write the equation down. No matter what value you put in place of y, x keeps getting bigger and bigger and bigger. And so whatever this fraction is, it's going to be something like, we got some number in the top over something that's getting closer and closer to infinity. Basically what this is showing is that the slopes keep getting closer and closer to 0. It's more of it like as a limit. As x goes to negative infinity, the slopes keep getting closer and closer to 0, and you can actually see that in the picture. This is definitely starting to level off as you head in this direction. In question 6, I want to take the derivatives of inverse trig functions by referring to these formulas. Let's start with this one, the derivative of arctangent of x squared plus 1. Well, here's the rule for arctangent. Arctangent of x has a derivative of 1 over 1 plus x squared. But this is arctangent of something more complicated. This means we have to use the chain rule. So to take the derivative, just to rewrite it so it's a little bit bigger, I'm just first going to pretend that that thing is just an x. And according to the rule, we do 1 over 1 plus that thing squared. So I just copy that thing down. But by the chain rule, I have to multiply by the derivative of the thing, and the derivative of x squared plus 1 is 2x, and this is my answer. All right, what about the derivative of this thing, x times sine inverse of 5x? The rule from the previous page for arcsine was the derivative of arcsine of x is 1 over the square root of 1 minus x squared. And sine inverse and arcsine mean the same thing, they're just different notations. If I want to take the derivative of this, I need to use the product rule because I have a product of two functions. So using the product rule, I start by taking the derivative of the first and multiplying by the second. But I then copy down the second thing and multiply by the derivative of the first. Well, the derivative of the first is the derivative of arcsine, or sine inverse, and it is equal to 1 over the square root of 1 minus, and it's not x, it's 5x, but that thing would go right here, like this. Now, because I have a 5x instead of an x, I have to multiply by the derivative of 5x, which is 5. And this is the answer here. The rule for the derivative of arc cosine, or cosine inverse of x, is negative 1 over the square root of 1 minus x squared. And this is only in the denominator. So I'm going to rewrite this problem as, this is really the derivative of arc cosine of x all to the negative 1 power. This way, I can use the chain rule to start this problem. I bring the negative down front, and I copy down the inside, and I subtract 1 from the exponent. I then multiply by the derivative of just arc cosine, which is equal to this. So I'm just going to multiply by that whole thing. And this is my answer. The derivative of arc secant of x is 1 over x times the square root of x squared minus 1. So if I want to take the derivative of this thing, okay, first, I'd have to take the derivative of just x. That's nice. That's just equal to 1. But then I add on the derivative of arc secant by using this formula. Wherever I see an x over here, I'm going to replace it with 2x plus 1. So I have this rule, why not use it? I get 1 over 2x plus 1 times the square root of 2x plus 1 squared minus 1. But this thing is 2x plus 1 and not just x. The chain rule says you have to multiply by the derivative of 2x plus 1, which is 2. And that is the answer. For this problem, let's note that the derivative of arccotangent is equal to negative 1 over 1 plus x squared. Okay, if I look at this problem, I'm going to rewrite it as this is the derivative with respect to x of x squared times inverse cotangent of, and I'll put x to the 1/2 power. I see here that we are taking the derivative of a product, and then within this piece, I'm going to have to use the chain rule. Okay, let's do it. The derivative of the first is 2x, and then I copy down cotangent inverse of x to the 1/2. I then add on x squared times the derivative of cotangent inverse of x to the 1/2. Applying directly into this rule, we get negative 1 over 1 plus x to the 1/2 squared. Now this whole thing must be multiplied by the derivative of x to the 1/2. And that is 1/2 times x to the negative 1/2. So because I have to put whatever is here in place of this x, that's why I have x to the 1/2. And this came from the chain rule, taking the derivative of this piece. And this is the final answer. The derivative of arccosecant of x is negative 1 over x times the square root of x squared minus 1. To take the derivative of this function, I'm going to use the quotient rule. So first, quotient rule says take the derivative of the numerator. That is negative 1 over x times the square root of x squared minus 1. Okay, I take this thing and I multiply it by the denominator, which is x plus 1. I then take the numerator and multiply it by the derivative of the denominator, which is 1. And this whole thing is divided by the denominator squared. Here's the answer. Let's prove this formula for taking the derivative of arctangent of x. What I'm going to do is write this as y is equal to arctangent of x. To say I want a formula for the derivative of arctangent is the same thing as looking here and saying, well, what is y prime? Like we're trying to figure out, well, what y prime is equal to. And I don't know from this equation. I do know that arctangent is the inverse function of tangent. So I can actually set up an equivalent equation. That equation is tangent of y is equal to x. Arctangent takes x to y. The inverse tangent takes y back to x. From this perspective, we can actually take the derivative of both sides of this equation with respect to x. Starting here, what is the derivative of tangent? Well, I know it's secant squared of y, and by the chain rule, you have to multiply by y prime. This is great. I mean, that's the thing I want to solve for. Here, x has a derivative of 1. In fact, we're basically done, right? I mean, y prime, the thing I want to know, is 1 over secant squared of y. Well, that looks like a formula, doesn't look like this one, and here's the difference. This one depends on x's, and this one depends on a y. What we're going to do is a little trick to change this so it is in terms of x. We're going to have to use a trig identity. The identity that I'm thinking of is, if you take sine squared of any angle and add it to cosine squared of any angle, it's going to be equal to 1, regardless of what the angle is. Here, the angle that is going into the trig function is y. So I'm just going to put a y here and a y there. Now, there's no secant squared that appears anywhere in this identity, but it's really easy to get secant squared. Secant squared is defined as 1 over cosine. If I divide this side by cosine squared, I'll have secant. I'll also divide this side by cosine squared as well. So let's see what that looks like. I'm dividing this side by cosine squared of y, and this side by cosine squared of y. I'm doing this because 1 over cosine squared of y is exactly what secant squared of y is defined to be. Secant is the reciprocal of cosine. Now over here, you can divide cosine squared into both terms in the numerator. Cosine squared into cosine squared is equal to 1. And here we have sine over cosine, which is tangent, but it's squared in the top and the bottom. So this is actually tangent squared of y. I'm putting this up here because instead of writing secant squared of y, I'm going to write tangent squared of y plus 1. Now, if you'll recall, this thing here, tangent squared of y, it's the same thing as, and maybe I'll write this down. So here's my next line. The derivative is 1 over, so tangent squared of y just means you're taking tangent of y and you're squaring it. But that's what we defined x to be equal to. X is tangent of y, so I can replace this with an x. And what we have is a formula for the derivative. It's now in terms of x's instead of y's. I mean, all I'm going to do is just reverse the order of the terms in the denominator, and this proves our formula. So the trick was, I set up y is equal to arctangent of x. I rewrote the function so it was written as a trig function that we could take the derivative of. What about proving this formula? The derivative of arctangent of cosine is equal to negative 1 over the square root of 1 minus x squared. What about this thing? Let's see if we can do a similar trick as in the previous part. I'm going to call this function arc cosine of x. I'm going to call it y. And what I'd like to figure out for this problem is, well, what's y prime? That's the formula for the derivative of arc cosine. What I'm going to do is rewrite this so I have it in terms of a function that I can take the derivative of. And that function is cosine. This is equivalent to saying cosine of y is equal to x. This thing here. One thing to note is that if you're using arc cosine and this represents an angle, I actually want to carefully state that the angle that we're using for y is between 0 and pi. That's how arc cosine or inverse cosine is defined. We'll see if that shows up later in the process. What I want to do is take the derivative of both sides of this equation. So starting here with cosine of y, well, the derivative of cosine is negative sine of y, and I have to multiply by y prime. And the derivative of x is 1. In fact, if you want to solve for y prime, that is 1 over negative sine of y. And this doesn't quite look like our formula, although, I mean, I see the negative is in front. Maybe I can, put the negative here instead of in the denominator. So this is negative 1 over sine of y. I think here it's written in terms of y. I would like to express my answer in terms of x. How could we do that? Maybe I'll go back to that identity that we used in the last example. Sine squared of any angle plus cosine squared of any angle is equal to 1. Okay? And here our angle is y. And we are saying y is an angle between 0 and pi. Great. Oh, I can solve this equation for sine by subtracting cosine squared to the other side and then taking the square root of both sides. Let's try it. So sine squared of y is equal to 1 minus cosine squared of y. Okay, excellent. If I take the square root of both sides on the left, we have sine of y, the very thing I want. And unfortunately, on the other side, you almost get 1 minus cosine squared of y. But technically, during this process, you get a plus or a minus. However, sine is positive in the first and second quadrant on the unit circle, and those angles are everything from 0 to pi. So the way arc cosine is defined, sine of the angle will always be positive. It will never be negative. So this is actually a great thing. I can just like get rid of that negative altogether, and that's because the angles are between 0 and pi, and that's where sine is always positive. So sine of y is, I'll just put the square root of 1 minus, and also maybe instead of just putting cosine squared y, I'll put, cosine y squared like this. This thing is equal to negative 1 over the square root of 1 minus cosine y squared, and cosine y is exactly what we called x. So I'll replace this with x. Y prime is equal to negative 1 over the square root of 1 minus x squared, and this proves our formula. All right, let's find the first and second derivatives for the functions in question 8. The first derivative is, well, for this function, I'm going to get 5x to the fourth plus 8x cubed plus 6x. And that is it. By definition, the second derivative just means take the derivative again. So we would get 20x cubed plus 24x squared plus 6. So here I have my first and my second derivative. Finding the first derivative of g of t is going to be 20t to the ninth plus 5t to the fourth. And the second derivative means take the derivative again. So here we get 180t to the eighth plus 20t cubed, my first and second derivative. The first derivative of f of theta is going to be cosine of 2 theta, and then by the chain rule we get times 2, or 2 cosine 2 theta. The second derivative of f with respect to theta would be, okay, we get 2. The derivative of cosine is negative sine of 2 theta, and by the chain rule we have to multiply by 2. And this would be negative 4 sine of 2 theta. Before taking the derivative, I'm going to rewrite this function as 2x plus 1 to the power of 1/2. The first derivative is 1/2 2x plus 1 to the negative 1/2 times 2. And if we simplify this thing, the 2 and the 1/2 cancel, and we have 2x plus 1 to the negative 1/2. The second derivative is negative 1/2 2x plus 1 to the negative 3/2 times 2, which is negative 2x plus 1 to the negative 3/2. The derivative of z of theta, the first derivative, we have to use the product rule. It's 1 times cosine theta plus theta times negative sine theta. And if I simplify this, we get cosine theta minus theta sine theta. The second derivative, z double prime of theta, is negative sine of theta minus, I'll set up some parentheses because we have to use the product rule. I want to make sure I distribute the negative. We get 1 times sine of theta plus theta times cosine theta. So the second derivative is negative sine theta minus sine theta minus theta times cosine of theta. And if we simplify this thing, that's negative 2 sine theta minus theta times cosine of theta. The first derivative of w with respect to z is, by the product rule, we have 1 times e to the 5z plus z times e to the 5z times 5. And it's better to simplify it before you take the next derivative. If I want the second derivative, Okay, I first get e to the 5z times 5 plus, I guess I'll use the product rule again. I could look to my previous work, but the derivative of 5z is 5 times e to the 5z. And then I have plus 5z times the derivative of e to the 5z, which is e to the 5z times 5. So just simplify here a little bit. We have 5e to the 5z, but we have it twice, so it's really, we have 10e to the 5z. And then we have plus 25ze to the 5z. Let's see if we can find the second derivative by using implicit differentiation. Let's see what that process would look like. For this equation here, if you want the first derivative, we would get 2x plus 4y times y prime is equal to 0. I'm actually going to stop here. We could solve this for y, but if we want the second derivative, we can just take the derivative of both sides once again. The derivative of 2x is 2, plus, and now I have a product. Product rule says that I need the derivative of 4y. The derivative of 4y is 4y prime, and I copy down the y prime. Okay, then I add on 4y and multiply by the derivative of y prime, and that's what we call y double prime. And that still is equal to 0. If I solve this thing for y double prime, that's the second derivative. I'll simplify this a little bit first. We have 2 plus 4, that's the first derivative squared, plus 4y times y double prime. Y double prime, the second derivative, is equal to negative 2 minus 4y prime squared, all divided by 4y. I'd like to write my answer without referencing the first derivative. I'm going to go back to this equation. I'm going to solve it for y prime. Let's see, I get negative 2x over 4y, which can be simplified to negative x over 2y. And I'm going to put that in place of this y prime. I get negative 2 minus 4 times negative x over 2y squared all over 4y. Definitely stuff here simplifies. Maybe I'll just take a second to write that out. Y double prime is equal to, okay, we get negative 2, then we get minus, that negative cancels, this 2 becomes a 4, canceling with that 4, and we have x squared over y squared. And this is all divided by 4y. We could get rid of the fractions within fractions by multiplying the top and bottom by y squared. And if we do this, let's see, we get negative 2y squared minus x squared all over 4y cubed. And here is an answer for the second derivative, and it only depends on x's and y's. For this problem, I'm going to rewrite it so I have powers of a half. So this is x to the 1/2 plus y to the 1/2 is equal to 1. If I take the derivative of both sides, I get 1/2 x to the negative 1/2 plus 1/2 y to the negative 1/2 times y prime, and this is equal to 0. I'm going to multiply both sides by 2. And that's to cancel the halves. Like, they're not really adding much to this question. So this is x to the negative 1/2 plus y to the negative 1/2 times y prime is 0. I could solve for my first derivative, but I'm actually going to take the derivative again of both sides of this equation with respect to x. And if I do that, I get negative 1/2 x to the negative 3 halves. I now have to use the product rule here. So I get negative 1/2 y to the negative 3 halves times y prime plus y to the negative 1/2 times y double prime. And y double prime is the thing that I'm solving for. This is the second derivative. I see that, again, I have the first derivative, but I can solve for that later from this equation here. Let's see, if I solve for y double prime, all right, what do I get? Basically, I'm going to move these two things to the other side of the equation and divide by y to the negative 1/2. So that is 1/2 x to the negative 3 halves. I get another plus 1/2 y to the negative 3 halves times y prime, and this is all divided by y to the negative 1/2. For brevity's sake, in this equation here, if you solve for y prime, we get negative x to the negative 1/2 divided by y to the negative 1/2. We would take this value, plug it in here, and it will take us to our answer, and I'll write that down next. So in place of the derivative, I'm putting negative x to the negative 1/2 over y to the negative 1/2. That is a great looking answer. Again, this is multiplication here. This could most certainly be simplified, but here it is, the second derivative.